we talk about the Deutsch algorithm. I won't go back again, but this is just a summary. There are two circuits because actually just two versions. This version has MSB at the bottom, and this one has an MSC at the top. You will see different version when you look at literature, right? So be careful. Always ask where is the MSB. If you still remember, the purpose of a Deutsch algorithm is that we will form a superposition. And this superposition in the x basis is just plus minus for these two qubits, right? But you can expand it. Basically, it is in order to get plus, we apply the Hadamard gate. In order to get minus, we apply the NOT gate first, right? Like here, 0, 1 becomes because MSB as a bottom, right? 0, 1, 0, 0 becomes 0, 1 because we apply the NOT gate to the LSB, these significant bits, right? And then we apply Hadamard gate, you get negative. In the quantum oracle, we encode the function that we are interested in. So let me remind you what it is. The quantum oracle get two sets of bits, right? In this particular case, it's only 2 qubits. What it does is just a unitary gate. Do you remember what it does, anyone? Or based on this figure, maybe you cannot see it. What happens when you apply this to xy in this particular case? It becomes what? X doesn't change. So I say again. Y exclusive or f of x. Okay, that's correct, right? So that's what it does, right? And then our goal is to measure in the plus minus basis. But in order to measure in plus minus basis, it is troublesome, right? Because the quantum computer already tuned to work in a certain basis. For example, to measure the spin in the up and down direction. It takes a lot of time to recalibrate or do other things. Usually what we do is just apply a Hadamard gate. You apply the Hadamard gate, then it's going to come equivalently. If you had a plus state, it becomes 0 when you do the measurement. If you have a minus state, it becomes 1 in the measurement. Then based on this measurement, if it's 0, I know it is a constant function. And if it's 1, I know it's a balanced function. Okay? This is the circuit that I asked you to draw at the very end of the class. Now, let's take another example, right? So now I try to implement the Deutsch algorithm in IBM Q quantum computer. If you look at this, you see that I have a NOT gate here. I have Hadamard gate. So this is the first part, step 1, right? And again, we remember that they all initialize to 0, right? So after this part, I do get minus and plus here, right? Which is plus minus. So this is to create the superposition. Make sense? Now the point is, where is the quantum oracle? Right? This is interesting. Where is the quantum oracle? If you look at this one, you find that it is step 2. And what do I have here? I have just 2 identity gates. So this is a very simple example. So what am I implementing here? Actually, here I'm implementing an oracle for f of 0 equal to 0 and f of 1 equal to 0. So is this a constant function or balanced function? No, this is what I'm saying. The f of 0 equal to 0, f1 also equal to 0. Because that is the output, remember? This is the input, this is the output, input, output. So it's as you said, this is a constant function, right? Then what should this oracle do if that is the case? Think about this. UF, right, XY. I just combine them together because you know that this is a tensor product. XY equals to XY exclusive or F of X, right? That's what it does for this quantum oracle. But what is F of X in this case? 0 is constantly 0, right? Because F of 0 is 0, F of 1 is 0. It turns out this is the function I try to evaluate, right? So what is this? If 0 exclusive or Y? It's always just Y, right? If exclusive with 1, 1 exclusive with Y, you get not Y. But 0 exclusive or Y, you get Y. So do you see that input is XY? After this quantum oracle, I get XY. So the implementation of this quantum oracle is just an identity matrix. Now you may feel this very strange. I mean, what is the point? This is just for demonstration. Because if I already can construct this explicitly, then I already know the function. Why do I need quantum computing? Right? So there must be a way for something very difficult that you can go through an algorithm. It will construct by itself, construct the gates for you, or maybe just physically you can embed that Hamiltonian, that problem into the quantum gate. And that is the assumption in this quantum computer. How do you come up with the oracle? Remember, you don't know the oracle because you know exactly what it does. Then you know whether it's constant, right, or balanced. Or it's possible you know what it does, but it takes a very long time to compute, right? You know all the circuit. Let's say there are 10 trillion Langevin NOR gates inside the circuit. You need to simulate that. I don't know. Maybe that can be very fast also, or 10 trillion to the power trillion, for example, right? Then you can use quantum computer. But the question is still how you convert this to quantum computing oracle. Okay, so I'm not good at this. For certain oracle, I know there's some algorithm that can help you to construct, and there is under active research. Here, we just want to know the basics, right? So in your homework, I give you different type of function. You need to come up with the corresponding oracle to do the simulation. And the oracle that you need to do is that you need to fulfill this expression. This is a very simple one because turn out both are 0, then this oracle is just equal to an identity matrix. Make sense? Okay, and then finally I need to measure the MSB and most significant bit in the plus minus basis. Again, I don't want to measure in plus minus basis. I add a Hadamard gate. Then I measure in the 0-1 basis or the computational basis. So if I get 0, then I know that is plus, or it is a constant function, right? That's what we said here. If I get 1, then I know it's a balanced function, as we proved last time through this constructive interference. So I save this 1 to 1. So let's go back. With last lecture, we spent a lot of time to understand the classical register in IBM Q. How many classical qubits do we have here? We have 2, right? So I save it to 1 means I save to the most significant bits because I have 1 and 0 position, right? So because this is constant, what do you expect for the output? Should I get 0 or 1? Since this is a constant function. Yeah, maybe you forgot. What should I get when I do the measurement? 0, right? So here, just to show you, indeed, I get 0, 0, 0, because I have 2 qubit, 2 classical registers. So you will give me 2 value, but the least significant one is 0. So I get 0, 0. Simulation tell me that I only get 0, 0, right? So in principle, if I didn't know about what function I have, I successfully deduced that the function I have just tested is a constant function because it is 0. Right? But when I put it in a real quantum computer, which you will have, right now IBM only provide hardware, otherwise you need to do the simulation yourself using Jupyter Notebook. Sometimes I get 1, 0. Means sometimes I get 1. Why is there any suggestion? Isn't that this is a constant function? I should always get 0, but sometimes I get 1. Why? See? Noise, error. And that is exactly the reason. There are different types of error. First, preparation error. You think that I'm prepared in 0? No. How do you prepare something in 0? You either let it cool down, right, from excited state to ground state, but due to thermal distribution, Fermi-Dirac distribution, there's always a probability you think it cool down to 0 after a certain time, it is still at 1. Or due to excitation, alpha particle or gamma radiation from the universe. Every moment there are trillions, I believe, of alpha particle, gamma ray going through our body, even at this sea level, right? So they will go through the qubit also, or due to other noise. The gate, they are not perfect. We are not doing error-corrected gate. So what is the meaning of Hadamard gate? We have not learned the broad sphere, but what is the meaning of not gates? You rotate it from one point to another point, right? At the beginning, we talk about a little bit of broad sphere. The so-called of gates is to rotate the vector on the surface of the broad sphere. You need to be very precise, right? If I say I want to rotate 90 degrees, if you rotate 89.99999 degrees, it still is an error. And you can accumulate the error and amplify. And finally, measurement error. Measurement can also have an error. You thought that you measure spin up, it can be spin down, which we do not discuss here. We discuss in E274. But the way you do measurement is actually affected by the noise because the quantum state is, when we do quantum measurement, it's like that. I want to see whether you are on the left or right of this classroom. And of course, I just look at you. But the situation in quantum computing is like this classroom is so small, and even I'm standing on the left, maybe part of my body are actually on the right. If the noise is large enough, actually you cannot distinguish me whether I'm on the left or right. Something like that. Okay, so preparation error, measurement error, gate error, and also when you are here, you're waiting for measurement, there is a decoherence error. You don't do anything to it, the qubit will gradually lose its state. Right? So that's why now quantum computers are still so fragile, because there are too much error. So you will need to wait for error-corrected quantum computing, which we call it the fault-tolerant quantum computing. Okay, so this one makes sense. After saying so much, just want to tell you that if you do a real computer simulation and you don't see error, there's some problem, unless they are error corrected. But I don't think you can access to any of this at this moment, unless you are a very famous professor collaborating with Google or IBM. They have some test machine for that purpose, for research purpose. Okay. Okay, great. Any questions? If no, I want to